Welcome to the Explainer. So, I hear you loud and clear on this one. You reached out saying Chapter 4 of your physics textbook, the one covering motion in 2 and 3 dimensions, is incredibly dense, and you just want it taught in a way that actually makes sense. And you know what? You're completely right. Reading through those pages can totally feel like trying to decipher an ancient code, or maybe just a recipe for a headache. It's so easy to get lost in the weeds of all those formulas, but don't worry, you are in exactly the right place. My goal today is to strip away the confusion and break down 2D and 3D motion into intuitive, visual blocks that you can actually understand and remember. Plus, we'll be going through the exact page numbers from your PDF so you can follow along. We are going to conquer this chapter together. Here's our roadmap for today's explainer, designed to logically guide you through pages 62 to 81 of your textbook. We'll start with vectors and 2D kinematics, hit a quick checkpoint on kinematics concepts, and then move on to mastering projectile motion. After that, we'll cover uniform circular motion, relative motion basics, and finally, a final understanding check to make sure it's all sticking. Let's get right into it. Section 1. Vectors and 2D kinematics. All right, so far in your physics journey, you've likely been dealing with objects moving in a straight line, right? Forward, backward, up, or down. But the real world doesn't just happen on a tightrope. It happens on flat planes and in three-dimensional space. To describe that mathematically, we need a brand new tool, the unit vector. When you look at the textbook, you're going to see these letters I, J, and K, usually with little hats on top of them. Please, whatever you do, do not let those little hats intimidate you. They aren't wearing them to be fancy, and they aren't complicated variables that you have to solve for. They're literally just labels. I just means in the X direction, J means in the Y direction, and K means in the Z direction. Think of them as sorting bins that just keep our dimensions neatly organized so they never get mixed up. To see how we use those labels, let's look at how a position vector is mapped out on page 63 of your PDF. A position vector is essentially just an arrow pointing straight from the origin out to where a particle is located. But instead of just giving one diagonal distance, we build that vector using our independent unit blocks. We take a certain number of steps along the x-axis, a certain number along the y-axis, and a certain number along the z-axis. It's exactly like following a pirate's treasure map. Walk 3 paces east, 2 paces north, and 5 paces straight up. That overall arrow is just the combined result of those completely independent steps. Now, as that particle actually moves along a curved path over time, its position changes, and we get velocity. Jumping to page 66, we can see how this builds into the instantaneous velocity vector. The absolute crucial point here is that this velocity arrow is always, and I mean always, perfectly tangent to the particle's path. It shows you exactly the direction the object is heading at that exact split second, even if the overall path it's taking is a winding curve. Section 2. Checkpoint. Kinematics concepts. Okay, we've covered the basics of how position and velocity vectors work in 2D space, but let's make sure this is actually making sense before we add more complexity to the mix. This brings us to checkpoint 1, straight from page 66 of your text. Imagine a particle moving in a circular path. At one specific instant, its instantaneous velocity is v equals positive 2I minus 2j meters per second. The question is, which quadrant is the particle in, assuming it's traveling counterclockwise around the circle? I want you to test yourself here. Go ahead and pause the explainer right now, grab a scratch piece of paper, sketch it out, and press play when you think you have the answer. All right, welcome back. Let's walk through the logic on this one together. Looking at the components, the velocity has a positive x component, that's the plus 2I, meaning it's pointing to the right. It also has a negative y component, that's the minus 2j, meaning it's pointing downward. So our combined velocity vector points diagonally down and to the right. Now, if the particle is traveling counterclockwise along a circular path, for that tangent line to point down and to the right, the particle literally has to be located in the first quadrant of that circle. If you got that right, fantastic, you officially know how to read vector components. Section 3. Mastering projectile motion. Now we get to apply everything we've learned to projectile motion. This is your tennis ball flying over the net or a baseball hit out to the outfield. It's really the ultimate test of two-dimensional kinematics. And on page 72 of your PDF, there's a stroboscopic photograph that reveals the absolute biggest secret to solving these problems. It shows a yellow golf ball drop straight down and a right golf ball shot horizontally at the exact same time. Notice how they perfectly align horizontally at every single time interval on the way down. The fact that the red ball is moving sideways has absolutely zero effect on how fast it falls. The big secret? Horizontal and vertical motions are completely 100% independent of each other. I actually like to call this the two projectors analogy.
Imagine one projector on the ceiling shining a light down on the ball to watch its shadow on the floor. That is your horizontal motion. It experiences zero acceleration, so it just coasts along at a perfectly constant velocity. Now imagine a second projector on the wall watching the shadow move up and down. That's your vertical motion. It is in total freefall, experiencing a constant downward acceleration of gravity, or negative g. By splitting a tough 2D problem into two simple 1D problems, you make the math an absolute breeze.
To see how this looks all together, let's step back one page to the diagram on page 71. When we combine those two independent motions back together, we get this beautiful parabolic arc. Notice the horizontal arrows on the x-axis? They never change length. Now check out the vertical arrows on the y-axis. They shrink on the way up, hit 0 at the very top, and then grow larger pointing downward on the way back down. Put them together and you have perfect projectile motion.
Section 4. Uniform circular motion. Okay, we're shifting gears now from parabolas to circles. Uniform circular motion, detailed on page 76, happens when an object travels around a circular path at constant speed. But wait a second, if the speed is constant, is it actually accelerating? The answer is yes. Let's see why. Notice how the velocity arrow is constantly changing the direction it points as it moves around the circle. Remember earlier when we established that velocity has both a magnitude, which is speed, and a direction? Well, even though the length of the velocity vector isn't changing, the direction is. And in physics, any change in velocity means you absolutely have acceleration. We called this specific type of acceleration centripetal acceleration. The word centripetal literally translates to center seeking. Because the object's direction is constantly being pulled inward off a straight line path to form a circle, the acceleration vector is always pointing radially inward, straight toward the exact center of the circle, perfectly perpendicular to the velocity.
Section 5, Relative Motion Basics.
For this next concept, from page 78, we have to bend our minds a little bit. We're looking at the idea that motion isn't an absolute thing. It looks entirely different depending on who is watching it or what your frame of reference is. The textbook introduces some formulas that honestly look like an alphabet soup of subscripts, but we can simplify it into 3 easy steps. Step 1, figure out who your stationary observer is. We'll call them frame A. And who your moving observer is, frame B. Step 2, figure out how fast B is moving past A. Step 3, simply add the vectors. If you want to know the velocity of the particle from A's perspective, you just take the velocity that B sees and add B's own speed to it.
To really ground that concept, think about a scenario where frame A is parked on the side of the road, while frame B is driving past them. Both of them are watching particle P. Let's say it's a dog running ahead. Because frame B is moving past frame A at a constant speed, their measurements of where the dog is and exactly how fast the dog is running are going to be mathematically different. One observer's reality mathematically shifts to another's simply by adding that difference in their own speeds.
Section 6, Final Understanding Took.
Well, we've covered a ton of ground today, from basic vectors to projectiles, circles, and relative frames of reference. Let's do one last interactive pause to lock in these rules so you are fully prepared to crush your homework. Turning back to page 74 for review, this is checkpoint 4, and it tests the most fundamental rule of this whole chapter. A fly ball is hit to the outfield. During its flight, ignoring air resistance, of course, what happens to its horizontal and vertical components of velocity? Are they constant? Do they change? Go ahead and pause the explainer again right now, think back to our golf ball example, and answer the question. Okay, let's review. Remember the core rule here. Horizontal and vertical are totally independent. Therefore, the horizontal velocity remains completely constant the entire time because there is absolutely no horizontal acceleration. The vertical velocity, however, is at the complete mercy of gravity. It decreases on the way up, hits exactly 0 at the peak of the arc, and increases in the downward direction on the way back down. If you've got that conceptual separation down, you've officially conquered projectile motion. Which brings us to our final thought. We just learned that velocity is completely relative. How fast you're moving depends entirely on who is watching you. So I want to leave you with this question to ponder long after this explainer is over. If every single object's velocity changes based on the observer's frame of reference, is there any such thing as absolute zero velocity anywhere in the universe? Think about it. Thanks for joining me today and keep exploring.